everyone, welcome to the fourth lecture in the PLL series. In this lecture we will do transient modeling of all PLL blocks and then we will do transient analysis to get the final VCO frequency. So let's open one cell view in the already existing design. That cell view will name as transient model. Wait a second. Let me file, new, cell view, edit. Yeah, here we'll say PLL transient model. Instead of this, we'll choose schematic. Okay. So here we are going to use the ideal PLL blocks which are already available in AHD library. So we'll browse for those. So we'll choose AHD library, then phase. First block is our frequency divider, phase frequency divider. So here comes PFD. The next block was a charge pump. After this, next block is VCO. Since this VCO generates a sinusoidal output, but what actually we want is a clock or a square wave output. So we'll add a comparator which will generate square output from sinusoidal output. Okay, now we need resistance, one capacitance, then voltage controlled voltage source. I will explain you each block once we put all of them together. So next block will be some voltage sources, basically one ground, one VDD, and one we are going to use as V center. Okay, the last block is a frequency divider. So now we'll go one by one. First block we'll use it as ground. For that, In the second block we'll use it as VCC. The third DC source we'll use it as V center, which is basically one of the inputs of VCO. V center. Now what we'll do, we'll take one V pulse, which will act like a reference clock to phase frequency divider. So basically what we have learnt in our last classes, the PFD compares the reference clock with feedback clock. So feedback clock will come from frequency divider and it will go here. Then reference clock will come here. Then this PFD will generate two signals. One is up, one is down. Then charge pump will generate V control, which will find mostly then will which will finally go to loop filter, and then from loop filter it will go to this VCVS. Basically, this VCVS will generate a delta V, which will be multiplied with K VCO to give the final output frequency. So this delta V will go here, and other input will be control voltage, center voltage. First input is a control voltage. We will label one by one. So here reset we are using as VCC. And then this will go to comparator, which will basically convert the sinusoidal signal into a square pulse. So finally this will be fed back to here. Now we'll label each of the blocks. So first is reference clock and feedback clock. So basically uh, two clocks will be input to PFD, then it will give up signal and down signal. Then up signal and down signal will give a V control, and V control will be used to generate a delta V control. Okay, so DELT V control. Then delta V control will generate the final VCO sine, and VCO sine will be used to generate the VCO clock. So reference clock will come here, feedback clock will come and sit here, then up signal will come and sit here, down signal will come and sit here. This will be V control, this will be delta V control, this will be VCO, which is sinusoidal, and this is final VCO clock. So mostly we are done. Here we have, now we will assign the parameters to each of the block. This is VCO, This is V center. So now we'll start with our frequency divider, which is basically a Verilog A model. So this we are using some variable n. Our threshold voltage is 0.45, which is half of zero point 0.9 point or VDD by 2. Then V high is 0.9, V low is 0, V transient is 10 pico, sorry, 10 pico, V rise and V fall. And delay we are taking assuming at 0. So this is done. Next is our pulse input. Voltage 1 we are assuming as 0. Voltage 2 we will take it as 0.9. Period we are taking as 40 nanoseconds. Then delay time we will keep as 1 picosecond. Then rise time again same, because all these waveforms should be synced, right? So rise time and fall time will be same. Pulse width will be basically time period, which is divided by 2 minus fall time or rise time. Okay, this is done. Then we'll go to our basically we'll go to VCO. So this amplitude will be 0.9. This will be F center. Then VCO gain we have made a variable K VCO. Apply. Then we'll go to our PFD. PFD high we are assuming as 0.9, V low we will assume as 0, V transient we will assume as 0.45. Then delay as we have assumed same 1 pico, then 10 pico, then 10 pico. Then this will be I charge pump, and transient time will be 0.45, delay will be 1 pico, rise will be 10 pico, fall will be 10 pico. This we are assuming as some resistance variable RES. This we will assume capacitance variable CAP. Then we'll go to this sine out. We are assuming as 0.9. Sine low we will assume at 0. And offset will give at 0 for comparator. Okay. So we are mostly done with this. Now what we will do, we will launch ADXL and do transient analysis. So launch ADXL, create new, transient ADXL, new tab. Here we will add the test, transient model, okay. So now we'll put each of, so in last class, if you have saw the video of last class, there we have finalized uh, or changed C, capacitance C and charge pump current to adjust the bandwidth. So here we will use the same values. So capacitance C, which we have finalized as 35 pico, and the charge pump current ICP we have assumed was, or what we decided was 26 micro to get 1.25 megahertz as bandwidth. Then F center which we are designing for is a 2 gigahertz. So we are designing our PLL for 2 gigahertz. So that's why F center we are keeping at 2 gigahertz. So KVCO from our last class is 2.5 gig, and we have calculated was 80. Resistance again, which we have calculated was 8.29k, sorry 92k. Then VCC is 1.8 and V center is zero point 0.9. So basically total 8 values. Now what we'll do, we'll add transient analysis and we'll use a stop time of 20 micro, and we'll, okay, nice. Now what we'll do, we'll add all the outputs one by one. Now we'll simulate. Okay, looks like my memory is full. So here we have generated all the waveforms. Now what we are going to do, we are going to analyze each of the waveforms one by one. One more thing I have done is, what we have done, we have find out the frequency of VCO clock, which I can explain later. Let's plot the waveform. Each of the waveforms I will plot. Okay, it's not coming in one window. Okay, I hope my screen is visible. So now we'll analyze each of the waveforms one by one. Maybe we'll zoom out. Yeah. So first we'll see this feedback and reference clock. So this is feedback clock and this is reference clock. So how it works is, like if reference clock is the first incoming clock. Okay, maybe we'll delete all unwanted as of now. For ease of analysis, we are going to, then we can append those things. Okay, so now what we'll do, we'll analyze our up and down signals. Why I'm zooming it out? So ideally our down signal will always be a 0, but up signal comes when we'll see a rising edge of reference clock, and it will go down when we'll see a falling edge of feedback clock. Sorry, rising edge of feedback clock. So it will go up when it will see a rising edge of feedback clock, and it will go down when it will see a falling edge, rising edge of feedback clock. So basically you can see it, the pulses, whenever we'll see the rising edge, and the reverse is true for down clock. So here rising edge of feedback clock comes first. So here in this case you can see a down signal up, and then when rising edge of reference clock comes, the signal will down signal will go down. Basically reverse. So for rising edge of reference clock, it will generate a up signal. For rising edge of feedback clock, it will generate a down signal, and similarly it will go down for rising edge of reference clock. Again we can go and analyze. Uh, so this we need to zoom. Yeah, here in this case you can see clearly, you can see each of the waveforms. So here rising edge up rising edge will give a up waveform, and this will go down with rising edge of feedback clock. So I think this is pretty much clear. Then this up and down signal will generate so this up and down signal, what it will generate, it will generate a uh, what we'll say is up and down signal will generate a charge pump current. So now we are going to plot charge pump current, and that charge pump current will generate in turn a control voltage. So how the control voltage is generated, that we'll look upon. Basically we'll plot again, maybe with including control voltage. What we need is a feedback clock, sorry, reference clock, feedback clock, down signal, up signal, and control voltage. We'll do it in append mode. So here we'll see, maybe we'll separate the plots and we'll zoom in a little. So you can see the control voltage. If we'll zoom it out, you can see it as increasing exponentially and then settling down to some 700 millivolts. Okay, this is because the loop filter or control voltage is coming out of a loop filter. So loop filter will basically is a just a RC filter, so that because of that RC effect, it will slowly increase and gradually settle down to a stable voltage, that is 700 millivolts. Now next thing is we will plot delta VCO, delta V control. So delta V control, you can see, is basically the difference between center voltage. This is the difference between the center voltage. The center voltage was zero point 0.9 and control voltage. So this delta V control is fed as input to VCO. So now we'll see the VCO sinusoidal input, which in turn generates a VCO clock input. We'll plot basically both together. So now we can separate the signals maybe, and we'll delete all unwanted signal for our clarity. Delta V control we saw, up voltage we saw, control voltage we already saw. So now what we are seeing is, so this is the output of VCO block, and the VCO after this, which it is feedback to, this signal is feedback to our you can say this feedback sorry, this output signal of VCO is feedback to comparator, which will generate a sinusoidal or clock waveform. So now we will calculate the frequency of this waveform, and we will feed it as, and we will plot that also. So basically our target from this design is to get a VCO clock of 2 gigahertz. So let's see whether it is actually a 2 gigahertz. So we'll send this to calculator. We'll remove these unwanted things. Now we'll take a frequency, falling edge 0.5. We have kept the threshold as 0.5. Then we'll apply. First we'll see what it is calculating. Something went wrong, looks like. Okay, we'll do it again. Okay, nice. So all things are set. We'll just apply. Why it is coming two times? Okay, we'll try this as last time. Send to calculator. Hmm. So you can see the calculated frequency is initially 1.8, 1.5, and then finally it settles down to 2 gigahertz. So this will send it to our ADL, and we'll plot that also. So this is the our, maybe we'll delete some of the unwanted things which we don't want to see now. So our final target is to check the frequency. See, the final frequency settles down to 2 gigahertz. So basically from this model we were able to achieve PLL, means PLL or ideal PLL using transient analysis, which is generating a 2 gigahertz of frequency. So this is all. Thank you very much. Thank you all. We will, in next class we will see the noise analysis of each of the block before going to MOSFET level designs of the block. Thank you. Thank you so much.